Hello and welcome to this Red Hat tutorial on the OptaPlanner Workbench, in which we will show how you can utilize the Workbench to build a simple cloud balancing optimization solution using OptaPlanner. My name is Duncan Doyle. I'm the Technical Marketing Manager for the Automation Product Group at Red Hat, and in a few simple steps I will show you how you can go from an empty project to a full working application using OptaPlanner. OptaPlanner is part of the Red Hat JBoss BRMS offering, in which it's called Business Resource Planner. And to find more information about the OptaPlanner project, you can visit www.optaplanner.org. For more information about the Red Hat products and portfolio, I'll refer you to the redhat.com website. So let's have a look at the OptaPlanner website and what we can find on it. So we go to optaplanner.org. As you can see, there's a green button here which allows us to download the OptaPlanner distribution. There's also a section in which we can look for documentations. There's videos available, slides and trainings, as well as use cases. So use cases for a planner are things like cloud optimization, employee rostering, and vehicle routing. In this tutorial, we'll be looking at the cloud optimization use case, and we'll build a small cloud optimization solution using the Planner platform. So let's look at the cloud balancing domain and the problem that we're trying to solve. So the idea here is that we've got a number of processes that need to be assigned to a certain number of computers. These computers have certain constraints. For example, a computer has a certain amount of CPU power, it has a certain amount of memory, etc., etc. Second, the processes require a certain amount of CPU power and require a certain amount of memory. Finally, the computers have a certain cost. So it might be that a certain computer costs $13 per hour, another one costs $12 per hour. So the idea here is that, first of all, we need to place the processes on the computers in such a way that we don't overload the computers. And that would be, as we call it in Planner terms, breaking a hard constraint. We are not able, or we can't overload computers. And the second thing is that we'd like to minimize costs. So we need to assign the processes in such a way that the total cost of the computers required to run these processes is as low as possible. And this is what we call a soft constraint. So we've got hard constraints is to make sure that all the processes can run on these computers, and the soft constraint is to minimize the computer costs. Based on this information, we can now build a domain model. OptaPlanner is written in Java, and the domain model can be built using simple Java POJOs. In this case, we've got three classes that we need to define, as is depicted on this picture. First of all, we need to define the planning entity. The planning entity in OptaPlanner is the entity that OptaPlanner can play with. In this case, it is the process, because we need to assign the process to a certain computer. So while OptaPlanner is solving and is trying to find better and better solutions, it's assigning processes to different computers to see whether that solution has a better hard score and soft score. Remember, the hard score was whether it's a feasible solution, whether we're not overloading the computer, and the soft score was the computer cost that we want to minimize. So the planning entity is our process. The planning entity needs to be assigned to a computer. So in this case, the computer will be our planning variable. So we assign the process to different planning variables while the planner is solving the solution. So we've got a planning variable called computer. And the third class that we need to define is the planning solution. The planning solution defines both the initial problem that we want to solve, the solution that OptaPlanner creates, and the score of this specific solution. So let's first look at the problem that needs to be solved. So the planning solution contains a list of the planning entities that need to be planned, in this case a list of processes. The second entity it contains is a list of variables. In this case, it contains a list of all the available computers that we can assign our processes to. And third, it contains the score. So for every solution that OptaPlanner finds, it calculates a score, which is saved and contained within the planning solution. When OptaPlanner finds its, in this case, best solution, so if we terminate the solver, we terminate planning, it will return the best solution that it has found so far, again in the form of the planning solution clause, in this case the cloud balance clause. So let's get started and create an OptaPlanner project. Here I'm using the jbpm console or the KIE-Workbench. There are instructions in the comments underneath this video on how to get that environment up and running. So please follow those instructions and you can follow along the tutorial. So first we create a new project. We give it the name Cloud Balancing and the description Cloud Balancing, and we click on Create. So the platform will now create a new project in the underlying Git repository. So the next thing that we need to do is that we need to define our domain model, which means that we need to define certain data objects. The platform contains a data modeler that we will use to create our data model, which under the covers creates a Java Pojo based data model. Here we've created our process data object, as you can see here, and we'll now create the other objects as well. So we click on data object again, and we create the computer. Remember, the computer was our planning variable. The process is the planning entity. And we create a third asset, which will be the cloud balance solution. So now that we've created our three domain models, we need to create the variables or fields or attributes of these domain models. So let's look at computer. We'll give computer an ID so we can uniquely identify it. We give it a CPU, so that's the CPU power provided by this computer, and we'll give it a cost. In this simple demo, we'll only look at CPU power and not at memory, just to be able to finish this demo in a reasonable time. If you want to create a more complex demo, you can add the memory requirements and I/O requirements at a later point in time. So now we look at the process. So the process, we provide them with an ID as well to be able to uniquely identify those entities as well. We provide it with a field called required CPU, which is the CPU power required by this specific process. And we create a field called computer, which is our planning variable, and it is of type cloud computer, or of type computer that we just created. We now go back to the menu, the asset library. We click on cloud balancing solution. So we're going to add fields to the cloud balancing solution as well. In this case, we want to create a list of processes which contain our planning entities. So we select process as the type and click on list. We also need to maintain a list of computers, our planning variables. So we select computer and we click on list. And we need to also define a score, but that's done automatically by the platform when we configure the OptaPlanner properties. So we'll save this object for now. We'll now configure our domain model to be used with OptaPlanner. So we select the process, which is our planning entity. We click on process. We click on the OptaPlanner icon to open the planner settings panel. And we select planning entity to mark this data model as our entity. As you can see in the source, a add planning entity annotation has been added to the Java Pojo. Next, we select computer, which is our planning variable. We open the planner settings panel again. We select planning variable, and we'll give it a ID, which defines the value range ID for this planning variable. This value range ID needs to match with the idea in our cloud balancing solution planning solution clause, as it identifies the collection of computers that can be to which the process can be assigned. So we clicked on the cloud balancing solution in the OptaPlanner settings. We configured it as a planning solution, and we set the score type. As you can see, OptaPlanner supports multiple scores, but in this case we'll select the hard soft score, which is the default, because we have got hard constraints and soft constraints, 2 levels. Next, we define the computer list as the planning value range provider, and we give it the same ID as the value range provider in our planning entity for the computer planning variable. We save the domain model, and we can see that a new global score holder has been added of type hard soft score holder, which is the global variable for our rules to keep track of our score. Our score, as said earlier, is based on two constraint types. A hard constraint, which matches the hard score, and this is the constraint that must be satisfied by any solution for it to be a feasible solution. In our case, that means that the CPU requirements of all the processes on a computer must not exceed the available CPU of that computer. If it does, the solution is marked as infeasible because we break a hard constraint. The second score is the soft score, which matches our soft constraints. And soft constraints in Planner should be satisfied as much as possible, and better solutions satisfy more soft constraints. In this case, in this example, our soft constraint is to minimize the computer costs. So let's now create our score rules. Our score rules are defined in the rules language. So we're going to create a new guided rule that defines the hard constraints for the total CPU requirements of our processes. So we add a condition to a rule which says there is a computer, and we provide that with a variable name. We call that $C. Next, we add a restriction on the field, and in this case, we want to add a restriction to the field CPU, and we bind that to a variable as well. We now add a second condition on our rule that accumulates all the processes on a certain computer. So we select from accumulate, and we add the fact type number. Next, we add a pattern. In this case, we want to accumulate all processes, and we want to select all the processes that have been assigned to our computer. So we select computer equals 2, and we select a bounded variable called C, which matches the computer in the first condition of our rule. We now put another restriction on the field because we need to accumulate all the required CPU power of these processes, and we bind that to a variable called rec_CPU. We can now use this variable in our accumulate function. So we want to sum the required CPU of all the processes assigned to our computer, which we do with sum rec_CPU. We now click on there is a number, and we add a restriction using the expression editor. We say, well, the int value of this number, which is the sum of all the required CPU of all the processes assigned to this computer, if that is greater than the CPU power of our computer, then we want to add a hard constraint. So we click on the plus sign on the right hand side of the rule, and we select modify hard score. And we actually want to bind now the value of, or the total value of the required CPU. So we say total rec_CPU because we want to use that in our score calculation. Because our score calculation should not just say -1. In fact, the hard score that we want to add is the total required CPU minus the CPU power provided by the computer. So this gives us an indication of how much CPU power the computer is actually lacking to accommodate for the processes assigned to it. And we save this rule. We now go back to the asset library and we create a second asset, which is again a guided rule, but now a guided rule that defines our soft constraint, or our computer costs in this case. So we create a new guided rule and we add a constraint which says there is a computer, and we bind that to a variable again called C. And now we add a second constraint which says the following exists, because we want to know all the computers to which at least one process has been assigned. So we say the following exists. There is a process for which the computer is equal to the computer that we defined in our first constraint. So if that is the case, that means that that computer has at least one process assigned to it. And if it has one process assigned to it, we have to use it and we have to pay for that computer. So we now add a soft score which defines the cost. So we need to bind the cost variable or the cost field to a variable so we can use it in our soft score, and we say minus cost. So the soft score is the negative of the costs of our computer, and we save our rule. So the next thing that we need to do is to create our solver configuration. We can do this by going back to the asset library and say create new asset, and we say solver configuration, and we give that a certain name. In this case, we call it cloud balancing solver configuration. Click on OK. And here we can see the knowledge base and the knowledge session of drills that we want to use. We keep that as a default. We haven't configured anything specific. But we can also set the termination of the planner. So what this means that it states that the solver will terminate after 30 seconds. If we don't configure this termination, it will keep solving forever until we give it a stop command. We can configure the construction heuristic. In this case, we set that to first fit. And we can also configure the second phase of the solver, which is the local search, which we set to late acceptance. And we save the solver configuration. We need to know the name of the solver and the package in which it has been defined. We'll need that later when we create our solver in our decision server. And we can now build and deploy our project, which means that the project gets compiled and it gets deployed onto our execution server with planner capabilities built into it. So from the menu, after the build has been successful, we select the execution server tab, and we can see that our cloud balancing project has been deployed on our default key server, and that the deployment is green, so it's available. We can now open our Postman REST client, and the first thing that we need to do is we need to create a solver in our cloud balancing container running on our decision server. So here you can see the RESTful request that we're firing at the server. It's going to be a put, and as I said, we need to keep track of where the solver configuration is because we need to provide that in the RESTful request. We're creating an application XML content type, and we're using the extreme marshaller within the decision server. So we say send, and as we can see, we get a 201 created, and which means that the solver has been created in our decision server. We can now send it our cloud balancing problem that needs to be solved. Again, we're using the extreme marshaller, and we have to define the XKey class type of the cloud balancing solution of our planning solution that we're going to send. Looking at the body of the request, we can see that in XML we've defined 4 processes that need to be planned. They all have an ID and the required CPU for that process. And we've got 3 computers, all with a certain CPU amount that they provide and a certain cost. What we can also see is that these processes have not been assigned to a computer yet. They only have an ID and a certain required CPU. So we now do a post of this problem to our solver and we get back a 200 OK, nothing more. This is because the planner is now solving this problem in the background. So we do a get on the solver and we can see that the status of this solver is set to solving. It will keep on solving until it terminates, which will be 30 seconds as we have configured in our solver configuration. The response also contains the current score of the best solution that planner has found, apart from the status. We can now see that the planner has stopped solving, so the status is set to not solving. And we can now actually retrieve the best solution that the solver has found so far using the best solution resource URL on the solver. And this returns the domain model, so all the processes as well as the computers that they have been assigned to. So in this case, the first process has been assigned to computer 1, which has a cost of 300. We can see that the third process has been assigned to computer 2, which has a cost of 500. And the second and the fourth process have both been assigned to, again, computer 1. So we're using 2 computers here, computer 1 and computer 2. Which have a cost of 300 and 500, which add up to a minus 800 soft score. 300 plus 500 is 800 and we use the negative of that. And we've got a hard score of 0, which means that we're not breaking any hard constraints and the solution is feasible. And that concludes our tutorial on OptaPlanner, the OptaPlanner Workbench, and the cloud balancing demo. Here's a list of resources that you can consult to get more information about OptaPlanner, the OptaPlanner upstream community project, the Red Hat JBoss BRMS Enterprise offering, which includes the OptaPlanner platform, and the BRMS offering is called the Business Resource Planner, as well as my project source code for this specific demo, which you can find in my GitHub repository. Thank you for watching this video and good luck solving your constraint satisfaction problem with OptaPlanner.